Привет! Сегодня хороший день, и сегодня мы будем читать об компьютерной архитектуре. Итак, I'm gonna be reading this, and then I'm gonna be trying to look into Verilog UDP handling cores, maybe some NASDAQ 5 itch handling cores, and I might also go back and do what I was doing a few streams ago. Get like a sound check over here. 5 itch handling core. Sounds on. So a few weeks ago I did this Gleam one. That was already 7 days ago. Well, so a few days ago I was trying to solve this Gleam dependency resolution issue. So I might go back at the end, but in general the focus is going to be on this networking stuff. So let's just see how long this is. We're at 6:06. Dang, this is almost the end of the book, bruh. 650 still in. So that's probably the last chapter. Let's get to 680. Still in. These are the questions that we've... I don't know. Wow, this is the last chapter, bro. So this won't be finishing the book. Because... Oh, wait. 650? 605? 6. Okay, so we won't be finishing the book because I got to go back and read the chapter on file systems and the chapter on I/O, I believe. If I go to like page 2. So yeah, 3 red, 4 red, 5 red, 6 red, 7 red, 8 red, 9 red, 10 no, 11 no, 12 yes, 13 I'll do today. We can hit 14 as well. And then we're going to go back and read 11, which is... So 10 and 11 together are about the size of what we just read. So maybe tomorrow I'll do 10 and 11. And maybe 14. Networks programming with Unix sockets. I don't think I have that. Maybe I do. So, back to 606. So we're going to read this. This is like basics of computer networking. Just as a like lowest common denominator setup. And I'm going to get something to drink or eat before I start doing this. Classic water. Some Cheerios. I'm gonna need another one of those. Alright. Just checking. We got this on. And we're good. Alright. Fundamentals of networking and network protocols. No connectivity to the internet. Would we consider such a computer fully functional? Yeah. It'd be nice if they just define what these were instead of just giving them by this analogy that I'm gonna have to relearn like what they actually want these to be in the end anyways. Dude, I wish I had land throughout my home. We just talked about what? The protocol stack. Oh, so this is still talking about the protocol stack. Application, transport, network link, physical. Application layer does applications. TCP is a reliable and in-order byte stream. User datagram protocol. This one's transmission control protocol. User datagram protocol. No connection. No order. No guarantee. So transport layer does transport. It's gonna collat the packet. It's kind of crazy. So the network layer does networking. No, I don't skip. Alright. That's solid progress. So, I guess I just keep reading here. I'm kind of in the mood to do something more active. I'm getting kind of tired. Let's see where we're at. 1313 application layer. Transport layer. Stop and wait protocols. Pipeline protocols. So transport layer is a lot. About network congestion. Sliding window. You get to TCP. So we're going to be on the transport layer for a while. Whoa, I just messed that up. And it's 618. I'm goaded. So I'm in the mood to just do some programming, like honestly. So I'll leave this open. What if we come back to this? No, let's just do something real quick. Also, maybe I should move my camera to the bottom right. We'll see. CD punt. Get pull. See anything happened last night? Project. P. Nothing crazy. So. So we're gonna need a UDP handler. We're gonna need a lot, bruh. So let's move this one more. Let's open Vivado. So I want to write a TCL file. TCL file. Silex. Dude, I hate this like automatic moving thing. I'm not trying to learn this whole language, dude. I'm just trying to make a little file, bro. We can just open this. Better yet, we can go run TCL script. Front engine Vivado scripts. Did I not run it? Engine Vivado scripts TCL. Okay. TCL console. Huh? Because it already exists. It does already exist. Open. Vivado. Project. XPR. Huh? We can just upgrade it. So let's try adding designs for us. from Untension HDL system Verilog. Let's just put this in here. So I'm gonna want a BDF. How do you make a BDF? You go to design sources plus no IP catalog. Nothing for UDP. What about ETH? So there's this Ethernet core. How do you make a BDF file? Create block design. Design one, look at a project. Design one. So we're gonna want this in here. Yeah. Cannot add, why not? We're gonna add. Moving. Why not? The design source. Refresh the hierarchy. Dude, why the So you're supposed to just do it in the Verilog, it seems. People are suggesting. So it seems like people don't like it when you do. Hmm. You just use commands to connect them all together. Or not commands, just like TCL. Hmm. This is kind of difficult, dude. That's my part number. Hmm. This is just super useful Because we'd have this and this. You get all your pins. Okay. So I need to get all the pin constraints. Huh. Once we take this off. So, getting more into this involves pulling up IP I can't share. Шесть-семь, да. Yeah. So pulling up that is going to pull up the stuff I'm not supposed to be sharing, technically. And read more of this. So we got Axie. We got IP. We got UDP. IP, UDP, IP. RX. That's this. UDP 64. This UDP mux. Count data width. Keep enable. Keep width. ID enable. ID width. That's enable. That's width. User enable and user width. Turn off dead path. Already signal on selected port. Position of the clock. Let's begin. Select patch next. Something on the next in there. Redoing on the next again, update that logic. Sync ready state to source. Huh. Like, how do I learn how to even make this? How does this guy know how to make this? What? Oh. Hmm. Huh. Yeah, I can't really do too much on that in particular. And all that's super proprietary to this. Should probably consider doing my constraints. Yeah, man. Not actually going to the bathroom, but effectively. Solid. Tepier. Alright. Honestly, probably just go back to reading this. At least I'll read this application there part. So you got client server. HTTP, simple mail transfer protocol, standards independent of the platform. I think I was planning on reading that. Yes, sir. Gary Wright. By Gary Wright. I'm on volume 2. TCP/IP standard volume 2. Gary Wright. What about TCP/IP, which are the protocols? Captain Stevens. Oh, that's volume 2. This is the implementation. This is just the protocols. It's interesting. It's 1,000 pages. What happened to 200 pages? You bite. So, protocols and you got the implementation. Maybe we'll read that one. What's more urgent is these two, which are... I'm probably going to read this on stream. Started reading this. This is my current night book. I haven't even started reading this, so I kind of need to update this. Um, this I'm like halfway done with. This I'm probably not gonna read anymore. This I started but haven't finished. This is what we're reading right now, so we'll finish this week. We'll finish the Verilog book this week. And we'll finish this year, and this year, and this year, and these two this year. So I still have about 5 books coming in. 2024 list is gonna be kind of crazy, bro. You can see, like, this is kind of when the first year I actually like started doing stuff. Like, stopped just being like trash, honestly. Going back to 2020. To be fair, I did delete all my old repos effectively, so this is a bit scarcer than it should be for real. Okay, yeah, I definitely deleted some repos in here. 2022, this is when I started doing. This is when I first came to Georgia Tech. Working on my portfolio. First repository, yeah, that's false. Dang. Yeah, I remember working on this. E-code. Working on E-code. Wow. 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 2023. Some more deleted repos. MF Chess. The Web Dev Club. Working on the portfolio. This is my study abroad. Yeah. Yeah. In transient. Some juice stuff. MF Chess. I don't even know what private repositories would be. Oh, so this is like when I was getting back into program. This is like when I was getting. Dang. This is a year ago. First started recording, or that's just my DAW files. 2024 is when I started doing stuff. Internship here, I still would have had like things every day. Screw. Let's do screw. Wow. That's pretty crazy. I've kind of came a long way this year. This is the year I was like, I'm actually trying to get good at programming. Reading this, I remember reading, yeah. This semester is these 3. Like all of these projects for this year, getting into Queen, writing Gwipe, starting Punted, and starting Request. Well, I'm getting kind of good for, like, I'm actually getting kind of solid at programming. It's kind of crazy. So yeah, application layer is obvious. Transport layer. So you have a send, a receive. So the transport layer, arbitrary data size at the application level in order delivery. I guess in the TCP case, show the application from loss of data. I guess in the TCP case, show the application from bit errors and transmission. I guess the checksum. The transport layer may view the data from the application layer either as a byte stream or as a message. Byte stream for the win. Correspondingly, the transport may be either stream or connection oriented. This is connection oriented. Wait. I'm assuming this is saying this is connection oriented and UDP is just stream oriented. Or like a WebSocket stream. Yeah, I don't know what I'm talking about. In which case the application data is considered a continuous. Oh wait, this is saying it's the same thing. Right? Stream or connection oriented. The transport layer chunks the data into predefined units called segments and sends these segments to its peer at the destination. Okay, maybe. So alternatively, it can be message or datagram oriented, which is UDP, in which case the application data is treated similar to a postcard. Stop with these analogies, bro. To keep the discussion simple, we will simply refer to the unit of transfer as a message. The transport layer at the source has to break up the data into packets commensurate. See what that means? In proportion. The transport layer at the source has to break up the data into packets in proportion with the hardware limitations of the network. Correspondingly, the peer transport layer at the destination has to assemble the packets. That is called a scatter gather. That makes sense. The packets may arrive out of order. The transport layer at the source gives a unique sequence number for each packet. Sequence number helps in the reconstruction of the merger message at the receiving end despite the order of arrival. Thus, attaching a unique sequence number to each packet takes care of the first two problems with network communication. I need to thaw on my ground beef. Unique sequence number takes care of the first two problems. The source needs confirmation that the destination did receive the packets. Recall that there could be packet loss. As far as the transport layer is concerned, the packet did not make it. There's nothing mysterious. Dude, what are these analogies, bro? Electrical interference. Bit errors. Excuse me. Should be mentioned that such bit errors do not always make the packet completely unusable. Error correction, forward error correction when bit errors occur. The errors are beyond the fixing capabilities of forward error correction. The packet is good lost. Protocol should be able to recognize packet loss. You can use positive acknowledgement. Unique ID. Round trip time. Round trip time is the time it takes for a small infinitesimal message to be sent from the sender to the receiver and back again to the sender. Round trip time serves as an estimation of the cumulative delay time experienced at the sender for sending a packet and receiving acknowledgement. Depends on a number of factors: the distance, querying delays, queuing delays, makes sense, and message processing overheads. You have a network, yeah. There are some important differences. First, the post office delivers the acknowledgement to the end user. The analogous entity to the post office is the transfer layer. Dude, stop with the post office, bro. The acknowledgement stops there and does not go with the application. That makes sense. In the case of the postal service, the message is delivered in its entirety, and there is just one acknowledgement of the entire message. In the case of a network message. Dude, what is this postal crap, bro? In the case of a network message, this is just confusing me, bro. In the case of a network message, the transfer layer breaks up the message into several packets. There are a number of choices how to do this. Yeah, this just interjecting about like post offices in the middle of the thing does not help anybody, bro. Stop and wait protocols. So, simpler approach. So the problem we're talking about is that you have to break messages into packets. So the sender sends a packet and waits for acknowledgement. Once you get it, I guess once the receiver sends acknowledgement, just with what packet it is. Sender waits for a timeout period. If the timeout exceeds, then it retransmits the packet. The destination may retransmit the ACK. Such protocol as stop and wait, since the sender stops transmission after sending one packet and waits for an ACK before next packet. Stop and wait is trash. How many packets need to be buffered in the protocol stack of the sender for reliable transport and stop and wait? One? Yeah. Let us understand why you need sequence numbers in the first place. You have to know which packet you're acknowledging that you received. It's quite obvious. But thank you for not talking about post offices and explaining that. Alternating bit protocol. Let's see if we can choose the timeout parameter. So, question unanswered. Data flow of ACK, is that this? That's below. The data flow and ACK. The flow of data and ACK packets between the sender and receiver. Stop and wait. RTT is round trip time. Sender has to wait for the round trip time after transmitting a packer to receive an ACK. Shut out editors. Then it is ready to send the packet, and so on. Seems legit. The message has 10 packets and the round trip time is 2 ms. Assuming that the time to send receive the packet and the ACK are negligible compared to the propagation time on the medium. No packet loss. How much time is required to complete the transmission and stop and wait protocol? 10 packets. Round trip time is 2 minutes, 20 milliseconds. Pipeline protocols. So yeah, the virtue of the stop and wait protocol is simplicity. However, it sucks. The network is reliable, we can pipeline it without waiting for X. Message has 10 packets, and the time to receive a packet from source to destination is 1 millisecond. So, pipelining? Are you sending them bundles, or just literally sending them all at once? Oh, just constantly sending them? Take 11 milliseconds? Or, that's negligible, take 10 milliseconds. One millisecond. Time to send a packet is 1 millisecond. Time to send 1 packet is 1 millisecond, but the time to send 10 packets is not 10 milliseconds. But where's it like parallelized? Pipelined. Each packet is reliable. We blast all the packets in the message, one after another. Yeah, I don't even know if I like that. It takes 1 millisecond to send one. Send them all together. Yeah. I'm done. I see what they're saying now. Do you even need X? No. Reliable pipeline protocol. Source sends a set of packets. I just got flashbanged. The source sends a set of packets before expecting an acknowledgement. Acknowledges each packet individually as before, but the good news is that the sender does not have to wait for acknowledgements. Yeah, so this, you send 4, wait for 4. Send 4, wait for 4. Round trip time is how long you wait, but it's divided by your window size. See, it always makes it look like it's sending the first one as it receives it. Oh, okay, I guess it is. Network congestion. So there's only some at the begin with. Is that how you spell that? No, I thought it was one word the whole time. Wow. Smart Alec. I had never seen that. What is the origin of this? Okay. Random. Zero. You're welcome. It's also even. So now we're talking about sliding window. I've heard that as well. The message has 10 packets, round trip time is 2 milliseconds. Assuming that the time to send and receive the packet, and so the only thing that's not negligible is this. How much time is required to complete a transmission in the sliding window? It says a 5. So we're sending 5 at a time, so we're gonna have 5 total windows. It's 2 milliseconds, so 10. 4. Okay. 4. Yeah, wait. Distance from this to this. It's gonna have a width. It's got 1, 2. Right. You have 5 things. You have 10 things. You're going 5. You have 1, 2, 3. Wait. 1, 2, 3, 4, 5, 6 to hit all of them. So the distance from 0 to 0, the arc is 2 milliseconds. 2 milliseconds, and then we get here. It's another 2 milliseconds. So each window takes 2 milliseconds. That's all you gotta derive from that. Okay. TCP has cumulative X. One 156. Oh yeah, because you're gonna lose one of them. You're gonna lose 20% of those as well. Scheiße. 150 and then another fifth of that. And then another fifth of that. Oh, that's kind of interesting. 156. So how do you deal with transmission errors? We'll have UDP, transport layer summary, networking algorithms, distance vector algorithm. So how long, I feel like I've been reading this for like literal eons. No, dude. Oh my god. That's unfortunate. Dang, it hasn't been that long. That's unfortunate. The scroll is horrible. Transmission errors. Checksum. This guy really wants me to take an advanced course in computer networking. So transport protocols on the internet. I'm gonna take a break right quick. For real. Actually using this intentionally for once. Okay, noted. There you have TCP versus UDP. TCP is connection-oriented, self-regulating. Data flow as a stream, supports windowing and ACKs. UDP, no windowing, no ACKs. Connectionless, unregulated. Messages are datagrams. Excuse me. TCP pros, it's reliable. Arrives at, well-ordered, well-behaved. As in, it doesn't hog the network. Cons, a lot of complexity. At a disadvantage when mixed with unregulated flows. No guarantees. UDP pros are simplicity, no frills. Unnecessary features. Low packet loss and tolerant to packet loss. And it's unreliable, out of order, congests networks, no guarantees. Web browsers use TCP. Instant messaging, TCP. VoIP, low latency, UDP. Email, TCP. File transfer, TCP. Video over internet, usually UDP. Really? I would have expected it to be TCP. Yeah, I wouldn't really care if there's a delay on my Netflix, if there's just like some buffering in the beginning. Alright. File download TCP. Network file service. Oh, RMRF star came in after CDing into my dairy. RIP. Transport layer summary. The operating system supports several protocol families to cater to the differing communication needs of applications. I don't really care about any of that. Okay. Network layer. First glance, network layer is simple and straightforward. Send a packet handed to it at the source to the destination. Could be bundled in with the transport layer. This may not be a good idea. First, consider how many different network connections. Yeah. Thirteen 13.6? Where's 13.6? That's like 40 pages ago. You know, I'm going back to that. I mean, either way, I understand that. Intermediate nodes forward. Roots aren't fixed. So we're going to look at some routing algorithms. Dude, reading books is so OP. Reading something like this and reading something like data intensive applications, just like reading a bunch of junk in general, just like everything is connected to each other, and you can just like learn everything. Is kind of good. So there's a class. So you have Dijkstra's linked state routing. Vertices are hosts, edge are physical links. Link state is the cost. So you're just trying to find the minimum weighted path between two nodes. Local algorithm needs global information. Yeah. Okay, you can just like send, yeah. Two over AB square root. What is that? What is that? Is that a check mark? Distance vector algorithm. The lowest cost route of sending your packet to every destination in the network. Every destination in the network? Seems quite large. What is LS? Extras least. What is LS, bro? Link state routing, okay. Hierarchical routing. Yeah, I was curious a bit. Nodes on the internet as peers. Is this in capital for a reason? Gateway routers. Both the twin issues of scale and administrative control are dealt with nicely by organizing the routers on the internet into regions called autonomous systems. Within an AS, do LS or DV? Gateway routers are on the edge. Use a different protocol called Border Gateway Protocol. Makes sense. So these are ASs, and they use Border Gateway Protocol to connect between them, but they can use AV, no, DV or LA, link system, LS. So area code exchange number. Ooh. I thought TCP IP was an experiment. That's kind of crazy. That is. He thought TCP IP was an experiment. This guy's cracked. Genius. Velma. Что? Это неправильно, брать. Я уже сделал. Пожалуйста. Я это увидел. Я это увидел. Здесь. Да, я здесь был. Я был в Эстонии. Или это Литве? Я глупец. Виннис. Таллин, Эстония. Это Литве. Да, это Литве, конечно. Да. Я запомню, я здесь был. Да, я... Отлично. Очень круто. Виннис. Виннис. Это... Может быть, я это увидел. Что еще у нас есть? Да. И... Может быть, я это увидел. Да, это очень, очень красиво. Город. Да, это круто. Снегом. И он... Это в Советском Союзе, кажется. Вильне. Он музыкант или что-то, да? М. О, это очень круто. Да. О, нет, это очень круто. Yeah, this is like an abandoned prison. There's like a bunch of stuff in the middle. There's like restaurants and such. And you can just like casually tour it. It's kind of insane. Notable prisoners? Wow. Really? Wow. Wow. This is crazy, dude. Alright, get this out. Get this. Yeah. Wait, what? It was using the filming of Stranger Things? Really? Really? Where's that filmed? I don't know anything about Stranger Things, but... Dude. Curious if they actually used anything that's useful. Uh, yeah, it's so cool. Where's the... When did... Where's the Stranger Things? Is that it? Oh, yeah. Dang, I walked like right around all this. Dang, I forgot about most of this. Yeah, that's crazy, dude. No, I'm trying to go back to freaking Lithuania, bro. Lithuania is kind of goated. Alright, let's stop messing around, though. Alright. So, yeah. PQRS. It's 32-bit address. It's 8 bits. So the top 24 bits are an IP network. The bottom 8 are a specific device. XYZ0M. How many IP networks are there in this figure? Where's the slash, though? If you're assuming the slash is 24, then you got 1, 2. Yeah, none of them have the slash, though, so it's not really okay. Assume they're the top 24 bits. How many IP networks are there? You got 1, 2, 3. You got 3. Millions of IP network segments. It doesn't have to be 24 bits. They make multiple hops. And it looks like it's considering where it started to be a hop. Интересно. Circuit switching. Yes, I'm just skipping the analogies. Network resources in terms of bandwidth on these physical links are reserved once the call is established for the duration of the call. Circuit switching gives guaranteed quality service once the call is established at the risk of underutilizing the network. Underutilizing the network. Okay. Frequency and time division multiplexing. Never heard that. This is such a shallow chapter. Like, we're not actually really learning anything right now. Like, what have I learned in this chapter? UDP means user data graph protocol. I've learned there's like ways to interpret the like ways to like describe them, but not actually anything about what they do really. Please make a version without this. It's FDM and TDM. Frequency division multiplexing and time division multiplexing. Dude, this is akin to a postal service. Why does everything have to do with a postal service, bro? What happened to just explaining things using words? Okay, skip that. Virtual circuit is akin to making a telephone. So you can't learn this without reading this. The packet is individually stamped with the destination address. Look at the address to decide a possible address. Virtual circuit is a phone call. Datagram. So that's useless. Network routing versus forward routing. Dude. Network layer summary. Circuit switching. It's used in telephones, reserves network resources for the duration of the call. TDM, time division multiplexing. Supports multiple channels on a physical link than telephones. Frequency division multiplexing. Packet switching. So these are just freaking useless. Packet switching. A network layer technology used in the wide area internet. It supports best effort delivery of packets from source to destination without reserving any resources. Message switching. Same as packet switching, but your packets are just entire messages. Switch router. Device that supports the network layer functionality. It may simply be a computer with a number of network interfaces and adequate memory to serve as input and output buffers. Input buffers. Assemble incoming packets. Output buffers. So if you're buffering the output. Routing table gives the next hop to be used by the switch for an incoming packet based on the destination address. The initial contents of the table used by the network layer. Delays. So this is when packets. Everybody knows what a delay is. Store and forward. So delay waiting time for a packet to be fully formed in the input buffer before the switch can act on it, and then queuing. The waiting time experienced by a packet on either the input or output buffer because of other packets. Packet loss is when you lose packets, which has to drop a packet because the buffers are full. Service model is a contract between the network layer and the upper layers. You got virtual circuit, which is trash. Oh yeah, it sets up a virtual circuit, of course. They use a number instead of a destination address, and it's an index into a table that maps to the destination address. Datagram. No call setup or teardown. Each packet is independent of the others, and the switch gives you the best service model to deliver it to the ultimate destination. To conclude the discussion on the network layer, Let us comment on its relationship to the transfer layer. It is interesting to note that the intricacies involved with the network layer are completely hidden from the transfer layer. This is the power of abstractions, connectionless UDP, connection-oriented TCP in general. Okay. So quickly, link layer and LANs. Link layer. Requires the physical medium. I thought that was a physical layer. Or it controls the physical layer. Link layer deals with the frames. A network layer packet may require several frames. Random access and taking turns. Ethernet is random access, token ring is taking turns. Ethernet is the most popular link layer. Gaining access to the physical medium. It's the media access and control layer. What is this? There's always somebody beating on crab upstairs. Goat. I've never seen 10 sources. Is that 11? I think it's 11. I've never seen 11 sources for one sentence. Alright, let's get back to it. Media access control. So electrically, Ethernet is a cable that connects computers together. We use the term node to mean a computer or a host connected to a network. Nick. Connected via Ethernet. Ethernet cable is akin to a bus. This bus is not confined to a box, as we've seen in early chapters, but I can run through an entire building. Chapter 10, so I didn't read this, but bus arbitration is a scheme for deciding who gets the bus among competing components connected to it. In a bus that connects components within a box, arbitration logic decides who has the control of the bus. Okay, take your headphones off. Arbitration logic is the actual hardware that implements the bus arbitration scheme. Since there are a bounded and fixed number of units within a box, it is feasible. It's possible to do that. Oracle is trash. What does Oracle make that's like not absolutely shit? What do they make? Oracle database. MySQL. Wait, MySQL? They're acquired by Oracle Corporation? When did that occur? I guess I didn't really consider that to be Oracle. Wait. Well, Beehive, you get a bunch of business bloatware. You got HP, because everybody loves HP. You got, ooh, can't wait to download that. They own NetBeans? Oh wait, NetBeans. Oh yeah, nobody uses NetBeans. This made me think of JetBrains. This like Java based, and then you have like this upper camel, like this Pascal case type. ZFS, B-tree file system. Hardware. They own old servers. Oracle Cloud, probably the last cloud service I use. Services for lazy people. Oracle University. Inshallah, I'm not studying there. Yeah, I'm just being a hater. Let's just go back to the content. Okay. So this is possible because it's finite many devices. Further, the signals travel a shorter distance. Ethernet connects an... Oh, so this is in contrast to... Ethernet connects an arbitrary number of units together over several hundred meters. So how do you arbitrate among units with these problems? CSMACD. Carrier sense multiple access collision detect. Forms the basis of the arbitration of a broadcast medium such as the Ethernet. We keep the discussion of the protocol simple and superficial without getting too much into the detail. So we learn nothing. The designer of the Ethernet adopted this protocol to overcome the twin problems of distance and arbitrary number of devices. The intuition is that it comes from the way that we carry on a polite conversation. We look around to make sure no one is talking, then we will start to talk. If two or more people try to say something at some time, we'll shut up. Respect for using shut up. And try again when no one else is talking. CSMACD. Some acid. It's not much different from this human analogy. So, need to transmit. Shout out editing. Exponential back off. No context. Listen for carrier. Oh, so if you need to transmit, you do this. You listen for character. Medium idle. You transmit the message. There's a collision detected aboard the transmission. Until there's no collision. And you listen for carrier. Otherwise, transition complete. No, I feel like these are kind of ambiguous here. Let us dig a bit deeper into the protocol. Name and basic idea. So, CSMACD. So let me reread what that is. Carrier sense multiple access collision detect. A station wanting to transmit senses the medium whether there is an ongoing frame transmission. What? Where I feel like there's like 3 missing words in this sentence. A station wanting to transmit senses the medium weather. So it's saying it senses it whether or not there's an ongoing frame transmission, or it's sensing it to find if there is an ongoing frame transmission. If yes, then the station waits until the medium is idle and starts its transmission. If the medium is idle, it can start its frame transmission immediately. Absence of any electrical activity on the medium is the indication of idleness. Multiple stations sense the cable simultaneously for idleness. The multiple access term in the protocol comes from this fact. Thus, simultaneously, multiple units may come to the same conclusion that it's idle and then start their frame transmissions. This is a problem, and we'll see how we deal with it. Each station, after starting a frame transmission, listens for a collision. It knows the electrical activity it is causing on the medium. If what it observes is different from this activity, then it knows that some other station has also assumed idleness of the medium. That's collision detecting. Transmitting station immediately aborts this, sends out a noise burst to warn it that it's occurred. It waits for a random amount of time before repeating the cycle until it successfully completes its transmission. The algorithm chooses the random number for determining the amount of time the station waits before attempting to retransmit from a sequence that grows. The algorithm chooses the random number for determining the amount of time a station waits before attempting to retransmit from a sequence that grows exponentially with the number of collisions experienced. Dude, this is such a shit sentence. Oh. It's just like opening, like, I feel like I'm reading Lisp and like remembering it. It's like the opening of just 8 parentheses of like different like prepositional phrases that you can't tell where like this latter information which one they're applying to because the closing parentheses are obvious. The algorithm chooses the random number for determining the amount of time a station waits before attempting to retransmit from a sequence that grows exponentially with the number of collisions experienced during transmission. So the sequence grows exponentially with the number of collisions. So the station waits before attempting to retransmit from a sequence. What is a sequence? Yeah, I'm just gonna skip that. Exponential back on, whatever, dude. We define collision domain as the set of computers that can hear the transmissions from one another. Let us understand exactly how the frame is transmitted and how idleness of the medium is detected. Uses baseband signaling. The frame is transmitted digitally on the medium, directly as ones and zeros. Just as a point of distinction, broadband refers to the simultaneous analog transmission of multiple. Different services use different frequencies, respectively. Cable service, broadband. The same piece of wire simultaneously brings in your television signal. Oh, really? So you got IEEE 8023. So I'm not going to be... So it uses Manchester code. of the clock. That's quite technical there. So now you use a switch. There's no collision. 10 gigabit Ethernet assumes the host connected via switch links. Bitstream, so low, high, low, high, low, high, low. Wait. This goes from low to high. Or it goes from high to high. High to low. Low to high. High to low. High to low. Low to high. Low to high. High to low. High to low. This one goes from high to high. But okay. Wireless LAN and IEEE 802.1. Oh, this is for wireless. Collision avoidance. Ethernet features member of random access protocol family, opportunistic broadcast using CSMACD, exponential backoff on collision. Token ring is a member of taking turns protocol family. Token needed to transmit. Pros. Ethernet. Simple to manage, works well on light load. Cons. Too many collisions under high load. Token ring. Fair access. Works well under heavy load, but unnecessary latency for token acquisition and light load. Other protocols. Do I care about these? I'll just skim this, okay. Ethernet. Fiber distributed data interface, ATM. Fiber distributed data interface, fiber optic, especially suitable for banding Ethernet baselines together. It's a variant of the taking turns protocol. ATM was appealing, asynchronous mode transfer. ATM stands for asynchronous mode transfer. Am I dumb? Asynchronous transfer. Why would it be why would it be AMT? What the heck, bruh? ATM is appealing due to its ability to. Do people read stuff before they publish it? ATM was appealing due to its ability to provide guaranteed quality of service through bandwidth reservation on the links and admission control to avoid network regression. It is a connection-oriented link layer protocol and provides many of the network layer functionality as well that a transport layer protocol can be directly implemented on top of it. ATM is in presence in metropolitan and wide area networks. Link layer technology, PPP, point-to-point protocol. Dial-up, so it's trash. Gigabit, 10 gigabit. Networking hardware. It's kind of nice to know. Repeaters. Electrical signals decay in signal strength with distance because of heat dissipation and resistance. Repeater boosts the energy level of bits. Since land spread over fairly large geographical distances, repeaters are used to boost these signals and to overcome signal attenuation problems. Hub. So Ethernet is logically a bus. A hub is essentially Ethernet in a box. Ethernet cable, figure 1356, is replaced by a hub. A hub relays the bits received from one host to others. You can construct a more complex LAN. All the hosts are reachable via the logical bus formed by the interconnected hubs, for that same collision domain. Recall that the collision domain refers to the set of computers that hear the transmissions of one another. Therefore, computers connected to a hub have to detect collisions and follow the exponential backup phase, the Ethernet protocol, to resolve collisions to complete their message transmissions. A hub is essentially a multi-port repeater, and often the terms are used interchangeably. Collision domain, bridge between hubs. Bridges and switches. Switched Ethernet. Bridges and switches separate collision domains from one another. The data packets of host 1 do not cross the bridge unless the destination of one of the hosts is 3 and 4. So you can compare it in parallel. 1 and 2 to communicate in parallel with host 3 and 4. What happens when host 1 wants to send a message to host 3 while host 4 is sending one to host 2? The bridge recognizes the conflict and serializes the traffic flow between the two sides. A bridge contains sufficient buffering to hold packets when such conflicts arise. The hosts never experience a collision unless they happen to be in the same collision domain. The endpoints of the bridge, referred to as ports, pass packets to the other ports on a basis. Little union set type problem. Disjoint set type problem. I mean, I'm just gonna stop talking. Though bridge and switch appear interchangeable in the literature, some authors define a bridge as connecting a limited number of collision domains, whereas a switch is a generalization of the bridge supporting any number of collision domains. Switch supporting 4 collision domains. Okay. Switch. If you place all the hubs of switches, you get switch Ethernet. That's no question. Virtual LANs are a natural step. Next step for you switch Ethernet with switches. Virtual LAN. So can you say what a virtual LAN is? Wait, so what is a virtual LAN though? They're a natural next step. Okay. Network interface cards connect computers to networks. Half duplex. Every NIC has a MAC address used by the bridge for routing packets. Bridges automatically orient the MAC addresses of the NICs connected to them. Bridges and switches understand only MAC addresses. Packet looks as shown. Payload refers to the actual message intended for the destination node. Packet header contains MAC address of the destination node. To transmit a package outside the LAN, the node simply uses Internet Protocol IP. Packet, so you have routers. Router is on a LAN that understands IP addresses. Any node on a LAN that wishes to send a message to a node on the internet forms a packet as shown in 1338 and sends it to the router using the router's MAC address. The payload for the router contains a header for the actual message. Embedded in that header is the IP address of the destination node on the internet. As we've already seen, the routing has tables that would help it route the actual message to the node identified by the IP address. Address of router, so this is a packet, so you have a MAC address of the router and IP address of the destination of the message. 13.7 summarizes the terminologies and gadgetry that are common use today to identify. So, host, it's a computer on the network, it's a node or a station. NIC, network interface card, it is connects computers to the LAN. Port is an endpoint on a repeater hub or switch that connects to a computer. That is the physical layer. Collision domain is the set of computers that can interfere with one another. Repeater boosts electrical signal. Hub connects computers together to form a single collision domain, serving as a multi-port repeater. Bridge connects independent collision domains, isolating them from one another. Uses MAC addresses to direct the message on an incoming port to an outgoing port. Switch is similar to a bridge but supports several ports, so it's more ports. Provides expanded capabilities for dynamic configuring and grouping computers to VLANs. Router is a switch that can also route from the LAN to the internet. So this is what I was trying to find out. What is a virtual LAN actually? Virtual LAN. Capabilities in modern switches allow grouping computers that are physically distributed and connected to different switches to form a LAN. Virtual LANs make higher-level network services such as broadcast and multicast and internet subnets feasible, independent of the physical location of computers. Okay. So are you almost done with this chapter? Because this is kind of long, bruh. There's still so much left. You're trolling me, dude. I'm actually getting trolled. Dude, I'm actually getting trolled right now. This is a massive chapter. 93 pages. It's gonna be on like 650. Alright, let's pass this. 660. Okay, let's pass that 670. So I was on 63. So, dang, dude. I'm gonna be here for a long time. I've already been reading this for 3 hours. Like, that's crazy, dude. 3 hours? Insane. It's actually wild. I don't know why I'm reading that for 3 hours. Okay, so it's getting kind of cold in here. Ja, слишком mixed up. That's shout out to Nick P. The Nick P. Мы брать, мы брать. И так. Okay, what camera check type? Actually, I think it's fine, bro. It's good to me. So, I'll read more. I want to work on DMA lib. I'm in the mood to work on DMA lib. Casual NA Corona. Corona. It's a what am I feeling? Это неплохо. All right. So I'm in the mood to start working on this DMA stuff. Particularly this DMA library. So I kind of left off on this. It's kind of random. Kind of jippetish. So I'm hoping for a CLSP here. Imagine the CSP must be quite good. They have plenty of time to work on it. Though it doesn't seem like... Okay, that is working. So this is a BSG style. So this has changed. This pattern thing is no longer the case. Yeah, this isn't a thing anymore. So that's gonna change. So what do the tests test in this? This is only testing pattern, which was quite obvious. DMA. So how do you DMA? So C DMA. FPGA DMA. Yeah. So I'm not trying to hack people. That could still be useful, but let's see this. So this is a driver. Steam driver, let's see. So he's writing a Linux driver. Kind of dope. So again, I think this XDMA stuff. Hmm. So I'm just going to make a new scene. Duplicate this. Looking at IP. So we can remove all like the poop and grub. It's convenient. Okay, I can remove this. Also my camera. There's like a delay on it right now. It's like a one second delay. Not sure if I can do anything about it though. Could be is it a filter on next? I don't think so. Break. I am looking at IP. I'm looking at IP. IP image. What is going to be the first image when you search up IP? Yeah. IP. IP. Mess with this one. Wrong screen. Can you paste? You can't paste. Scheiße. Save as. Don't I have like images? Maybe doc image. Yeah. This is like IP pin. So we can load it in here as an image. This is going to be a new one. Browse. Doc. image. Huh? What? Oh. Doc temp, no, doc, cd doc, image. Yeah, boy, cd. CD doc. CD image. Let's move ipin, that, I think it was a JPEG. IP. AMD, Xilinx. Why can you not copy paste? Хочу убрать себя. .webp. That is scheiße. IP, AMD. What else do I want? Closed source. That's good. Why is it a WebP, bruh? Huh? .webp is the worst image format I've literally ever seen. Секундочку. Sorry, my mic was muted, but yeah, I just ate lunch and some stuff. But how is it 4 p.m. right now? I'm actually perplexed. Nah, I'm actually impressed that that was that long. Okay, wow. It's 4 p.m. right now. I'm looking at IP. All right, so yeah, I should probably start looking at IP. Let me add that other image in here. Only image IP 50 SD. Okay. I'm looking at IP. Хорошо. So I'm looking at IP. So now I'm not looking at. Well, actually, I'm about to start looking at IP. So if I do that, I'll close out these old tabs. Close. The link is in here. Did a casual email check. It is kind of nice having this like screen prat. Check the GT. Check the main. 38. -6. Build, confirm, prime. Getting rejected from Cockroach Labs. Getting charged for some bullshit. A bunch of advertisements. Okay, that's not exactly enjoyable. Purely mail. DraftKings. Some BS. Mostly just a bunch of BS. Может быть, я здесь. Это прошлым семестр. Кто она? Ебать. График 1. Динамика географической структуры российского импорта. Это трудно читать. Я 4 сделал. Chinese docs. Back. PCIe X DMA. This is what I'm trying to do. DMA bridge subsystem for PCI Express. So we have an FPGA end program, a PCIe card driver, and a PCIe host computer test program. Okay. Vada's FPGA. User bypass. Demo. PCIe. Excellent user bypass. User bypass. IP. So I think we need this. Put in tab. Open it. I'm unrawring this. Okay, so literally that did something. And there is a lot of stuff going on right there. So some of this has proprietary IP. Oh my gosh. Oh my gosh. So good. Flashbang. Давайте. I need to just not upgrade that. Or just run the right version. Yeah, I'll just run the right version. What? Obviously not 2 removed. Only want Lovato. Standard. So what kind of chip do I have again? I have an Arctic 7. What was Zyrinx? Dang it. Oh my god. This is hard, dude.
I feel like what I gotta do.
Let's just do crap. Alright, let's just take a break. Tired, bro. Alright, I'm just gonna finish reading this, close up my IP, work on other junk. Relationship between the layers of the protocol stack. What is that? Four times 6 minus 1500. Oh, the TCP/IP header. This is gonna be useful. Source and destination port. Window size field. Thin ac erg So I already did some examples on this. Processing delay at the sender. Transmission delay. Transmission delay. Message size over network bandwidth. Time of flight. Propagation delay is the time for the bits to travel on the wire. It's a function of distance. You get a queuing delay. It's on the switches. Processing delay at the receiver. So you got processing delay at the source, the sender, plus the wire time, plus the time of flight, plus the processing delay at the receiver. Throughput is the message size over the intent latency. So a message takes several hops. Between any two network hops, you have all these delays. See, I did these in lab a few days ago. This is all just one answer. Alright, so yeah, I did those examples in lab yesterday. So to summarize, the functionalities of the 5-layer internet protocol stack. The application layer includes protocols such as HTTP, SMTP, FTP. This is hypertext transfer, the mail one, and the file transfer. So the transport layer provides application-specific messages between two communication points. So TCP and UDP are transport. Network layer sends packets where they need to go. You got all those algorithms. Data link layer interfaces the network and the physical medium. So you have MAC protocols, Ethernet framing. And the physical layer, this is like the MAC and the like actual grabbing bits from like a physical analog setup or a digital setup into a electronic setup. Networking software and the operating system. So now we're talking about the socket library. This is the interface provided by the operating system to the network protocol stack. TCP/IP is the backbone. And it's instructive to understand some more about the programming of TCP/IP. So P1 connects a socket. If you look at the internet protocol stack, program was in the protocol stack shown. A Unix operating system provides a socket as an abstraction for processes to communicate from one another. The socket abstraction is agnostic to where the processes live. Same processor, different processors, or on a compiler, different boxes on a network. It's independent of how the bits move from process 1 to process 2. TCP/IP are vehicles for implementing the socket abstraction. Communication never goes in any external wire. So lower level issues disappear. The desired type of communication is another consideration. Design and implementation of the FreeBSD operating system. Packet arrival from the network. Network sends a packet into the NIC, which direct memory accesses it into memory. Int interrupts a device driver, which upcalls the TCP, which upcalls to the socket library. Implementation of the protocol stack in the operating system. So necessarily provide an implementation for different layers of the protocol stack to be network ready. The link layer is usually on hardware. You have an Ethernet card on your laptop. Mobile devices, wireless interfaces have become commonplace. Interfaces implement their own link layer protocols that are variants of the random access protocol as implemented by Ethernet. IEEE standards for the family of wireless WAN protocols are all derivatives of the IEEE 802, which Ethernet blocks. We had a glimpse of the CM. We had the avoidance versus detection thing. More advanced courses again. He's talking about more advanced courses. Same books every time. As you've seen already, TCP/IP is a dominant transport layer. Standard operating systems include efficient implementation of its stack. New research endeavors concerning operating system specialization and fine-tuning will use the protocol stack as a compelling example for new operating system mechanisms. Protocol stack is a complex piece of software and typically represents several tens of thousands of lines of code and several person years of software development by expert programmers. Yeah, that is true. Network device driver. Discussion of the operating support for the networking will be incomplete without a brief look into the network device driver. The network interface card allows a host to be connected to a network. A host may have multiple network interfaces depending on the number of networks it is connected to. Correspondingly, the operating system has a device driver for each NIC available in the host. Yes. As you mentioned earlier, a NIC usually incorporates some of the link layer functionalities of the protocol stack and hardware. The device driver for a specific NIC complements its hardware functionality to enable the NIC to complete the link layer chores. Chapter 10, we talked about DMA controllers for high-speed I/O. I should probably read that. A NIC incorporates a DMA engine to directly move in, out of host memory, out into the network. Data in, out. However, there's one fundamental difference between network and disk I/O. Data movement is in both directions, and disk is initiated in the operating system in response to some user-level system need. The network is certainly receiving, therefore the operating system has to be ready at any time. That's why you have a NIC. And an Ethernet NIC corresponding device driver incorporates the following functionalities: allocating and deallocating network buffers in the host memory, setting up the transmit network buffers and initiating DMA action by the NIC, registering network interrupt handlers, setting up network receive buffers for the NIC to DMA incoming network packets into the host memory, fielding hardware interrupts from the NIC, and if necessary, making up calls to the upper layers of the protocol stack. Figure 1343 captures the actions both in hardware and software for dealing with the network packet arrival. Since the NIC is made aware of the network buffers allocated for packet reception by the device driver, it can immediately use DMA to transfer the incoming packet into the host memory using those pre-allocated buffers. The NIC notifies the device driver about the packet arrival using the hardware interrupt mechanism of the processor. Using the upcall mechanism that we discussed in Chapter 11, the device driver alerts the upper layers of the protocol stack about the incoming packet. So yeah, there's more literature if you want. So Unix sockets. So let's look at it. Socket creation call in Unix takes on three parameters: domain, type, and protocol. Domain is a parameter that picks the protocol family to use. IP, if on the internet. Unix, internal, if the processor on the same machine or on LAN. This parameter specifies the application properties such as datagram or stream. Protocol, this is the protocol that runs with the federal family. Generality is the intent for providing the choice of parameters. There can be multiple protocols. One protocol. Protocol family is IP and the type is stream. Then TCP may be the only choice available as the transport. Separating those choices explicitly is an illustration of the power abstraction. 1342 paints a picture. P1, P2 are symmetric. Interprocess communication using sockets follow a client-server paradigm. Communication in socket made connection-oriented one or connectionless one. Type parameter makes this distinction. We'll just consider connection-oriented. So this is like TCP. And like in the establishment of the connection. It's making a phone call. Caller needs to know the number she's calling. The caller connects service anywhere. Yeah, so I know what that is. The server does the following preparation for interprocess communication. So the server creates a socket for communication. This has resulted in creating an endpoint of communication for the server. To make the phone useful, one first has to get a number associated with this phone. It's a name, also referred to as an address, a unique identifier associated with the socket. The system call to associate a name with a socket is bind. The intent is to communicate via Ethernet using IP. It has two parts, host address and port number. Host address is the IP address of the host. The port is a 16 bits unsigned. Operating system checked if the port is already in use. You have to kill -9 it if it is, huh? So, the operating system checks if the port number specified by the server is already in use. So now you have a name. Once bound, the name can be given to others who want to communicate with the server. So you have name servers. To receive a phone call, you have to plug the instrument to the wall so you can listen to incoming calls. Server side is the server to execute the listen system call. Tells you how many calls can be made. You accept receptions. I hate these analogies, dude. Just tell me how it works. Did I switch it over? Yeah, let's go. So, create a client card socket. This is the equivalent to getting a phone for the caller. To make a phone call, dude, stop. Please stop. The connect system call accomplishes the equivalent thing on the client side. Connects the client side socket to the name published by the server. So then the server's got to accept it. Client server are not ready. Call E, the accept system call on the server side accomplishes this analysis. Shut the fuck up about telephones. And the socket will recall that the server has already indicated its willingness to accept incoming calls on this connection. Therefore, the operating system completes the establishment of the connection between the client and server. Note that if you have a call waiting on the operating system provides the same facility with sockets. So now I have to read this. Note that if you have a call waiting on your phone, you'll still be able to know about incoming calls. So the operating system must do this as well. It creates a new data socket for the newly established connection. The operating system will implicitly queue up connection requests that may be coming in from other clients on the original name socket on which OS and calls into place. Summarize, you have these system calls. Socket to create an endpoint. Bind to bind a socket to a name or address. Listen to listen to incoming connections on a socket. Accept to accept an incoming connection on a socket. Connect to send a request name. To send a connection request to a name associated with a remote socket. And you establish the connection by creating a data socket for this connection if the server has already posted an accept system call. Receive incoming data on the socket from a remote peer. Send to a remote peer. So you're creating sockets. Server binds to a port and listens. The client connects to the port on the host. The server accepts. The client sends a data request. Server receives. Server replies. Client receives. Client closes socket. Server closes the data socket and goes back when they accept. So that showed the protocol between the client and server for establishing and making a message. Each time a new connection is established, a new data socket is created. It's determined by the lifetime of the connection. The listen call is a powerful mechanism for implementing a multi-threaded server. Indeed. Once a socket is created and bound, multiple threads can post accept calls on the socket. Multiple simultaneous client-server connections to be entertained on the same socket. Yeah. 13.5.2 shows the protocol between the client and server for establishing a datagram-oriented socket. The server is ready to send and receive a datagram socket as soon as it's bound to a port number. The client can start sending without the need for an explicit connect call. There are a number of issues. Can two processes communicate if the associated socket properties do not match? How does the server choose a port number? So there's questions that we don't know the answer to that you'd have to read the man pages or read a following book or read a following course. Yeah, okay. The operating system uses the appropriate transport protocol to implement sockets. It's beyond the scope, of course. Yes, indeed. Yep. We're encouraged to just read everything. Network services and higher level protocols. FTP, client server, host machine. You close it when you're done. You open a file. Here's RPC. Network file system exists on top of RPC. The FOPN call becomes an RPC call to the NFS server, which performs the file open system command on the name file residing at the server. How do you design RPC systems? And you gotta read more, so that was completely pointless to bring up, I think. Well, let's see. Summary. In this chapter, we cover the basics of computer networking. We reviewed the basic requirements for supporting network communication. Yep, we did indeed do this. It is responsible for running abstraction. TCP in order to delivery messages and such. Tension between fairness, reliability, and eagerness. Started. So this is. I did indeed read this. Don't really care about the particular section numbers. See, I did indeed read that. Indeed. Historical perspective. Yeah, I don't really care about telephones at all. I believe that. We got modems. What about Bell Labs? Really? Dennis Hayes. Computer. Inventor of PC modem. Nice. Evolution of the internet. So, yeah, pretty sure Al Gore just made the entire thing spontaneously. LAN, evolution LAN. I don't care about this at all. Fast Ethernet. Gigabit internet, Ethernet. Questions. And that's it. You got an epilogue. That's just a few pages. I'll go ahead and read this. Chapter 14. Processor design. We saw that high-level language constructs a key role. Summarizes high-level language constructs. So you got expressions, data types, hopefully algebraic ones, conditional statements. Yes, I know what programming is. It's pretty soon when we scratch the surface of the exciting area of microarchitecture. Process. The process concept serves as a convenient abstraction for remembering all the relevant details of a running program. Note that the processor can only run one program at a time. Operating system gives the illusion that each process has its own processor. You got traps and interrupts. Software algorithms. You got scheduling algorithms. You got traps. This book does really teach you a lot. I can't lie. This is a good book. As much as I hate on its analogies and such. So yeah, obviously it's more complicated. Memory system. Interplay between memory and OS. Fence register, bound registers, base only registers, paging. Dang, you actually learned a ton in this book. You learned so much in this book, dude. Like, this book will make you good at computing. And I gotta give it credit, because I mean, it takes five hours to finish a chapter, but it will actually teach you something. So reviewed all this: isolation, memory utilization, kernel and user mode, memory management policies. So yeah, some of these don't really use that much memory. Don't use that much hardware. Memory hierarchy, system about cache, translation local side buffers, parallelism, multi-core processors, threads. It's imperative for computer programmers. And IO, so I didn't really read this, but I'm talking about IO and DMA. I should probably read that for all. Persistent storage, file system, disk, study the design choices of systems. Disk is a medium. Networking, NIC, hub, switches, routers, bells and whistles, checksums, correction codes, packets, decoupling of packets across different layers, ordering, scatter gather, protocol stack. I'm just saying like every buzzword. Packet loss en route from source to destination, end-to-end acknowledgement of the protocol. Concluding remarks. Overall, the field of system architecture, the meeting point between hardware and software, is an intriguing and fascinating area. This area is unlikely to dry up for a long time since the application of computing in everyday life is growing by leaps and bounds. To keep pace with this growth and demand, the system architect has to continuously innovate and produce new computing machines that are faster, cheaper, consume less power, and offer more services. We hope this textbook serves as a launching pad for future system architects. That's dope. Nah, that's awesome. We hope this textbook serves as a launching pad for future system architects. Hopefully it does, Mo. Wow. That is a massive book, dude. When's the last time you read a 700-page book? Ramachandran. Oh yeah, I've seen this guy. That's awesome, man. All right. So, been on for just about 5 hours. I might end it here. Yeah. I'll probably do some more stuff looking at IP, and I just want to have this thing on all the time. So, I'm gonna end it. Yeah. Casual 5-hour session.